In section 3.3, we are doing some more truth tables. We're going to talk about conditional and biconditional statements, when they are true and when they are false. We've already introduced this concept when we first introduced truth tables in 3.1, but we're going to do a little bit more with it now. Conditional statements. So when will that conditional statement, if P then Q, be false? Consider an election where the first candidate, candidate A, makes the claim, if I'm elected, then I will lower taxes. So there are two different statements here. I'm elected is P, I will lower taxes is Q. P is our hypothesis or antecedent. Candidate A is elected. Q is our conclusion or consequent. Candidate A raises taxes. So the statement is false when he lies. If he happens to be elected and he doesn't lower taxes. Oh, look at that. That's a typo. I need to fix that. Lowers taxes. So fix that with me. If I'm elected, then I will lower taxes. Candidate A is elected is my hypothesis. Candidate A lowers taxes is my conclusion. If he's elected and he doesn't lower taxes, he lied. That's the case in which this conditional if-then statement is false. Okay, so candidate A is elected and taxes are lowered. In that case, both of those are true, and candidate A didn't lie, so the conditional statement itself is true. Candidate A is elected, taxes are not lowered. Well, this is where he lied, because he got elected, but he didn't lower taxes, so the conditional statement is false. Candidate A is not elected, so that statement is false. Taxes are lowered, that statement is true. Well, if he wasn't elected, he didn't have any control over the taxes, and so he didn't lie. That his original if-then statement is still true. He is not elected, false. Taxes are not lowered, false. Well, again, if he's not elected, he didn't have any control over the taxes, so he didn't lie. So the conditional statement still stands as true. And here is our reminder again. The conditional statement, if P then Q, is true in every case except when the hypothesis is true and the conclusion is false. That's the only case where that conditional statement is false. Let's build some truth tables. We have 4 different statements here, and we haven't introduced these terms, but we're doing that now. We're going to talk about the conditional, and then we can rearrange. Notice my conditional is kind of my base statement, if P then Q. Then I have the converse, inverse, and contrapositive, and they are all different types of conditional statements. My conditional statement, my most basic form, is if P then Q. If I reverse the order of the hypothesis and conclusion, I have the converse. If I take my conditional and I negate both statements, I have the inverse. And if I take my converse, where I have reversed the two, and negate both of them in that order, I have the contrapositive. Now, these 3 different types of statements are tied to our conditional statement. We're looking to see which of them are logically equivalent. Remember, logically equivalent statements have the same truth values in the same order. To try to remember which one is which, well, our conditional is our base form. It's the most basic there is, if P then Q. Inverse, in means not. If you can remember that prefix in means not. So I take my conditional and I apply the not. Instead of if P then Q, it is not P then not Q. Contrapositive is the longest, most complex word here, and so I do the most stuff. So I take my conditional statement and I not only flip the terms and change the order, but I negate both of them. So I do the most to the term that is the longest, that contrapositive. And if you can remember what those two are, then converse has to be the other one, where I just reverse the hypothesis and conclusion. Because we have 2 statements for each of these, each truth table has 4 cases. So let's kind of start setting that up. I've got case 1, 2, 3, 4. We're going to do if P then Q here. We're going to go ahead for the converse and we're going to look at it as if Q then P. We're going to reverse the order of those columns. For the inverse, cases 1, 2, 3, 4, we want not P and we want not Q. For the contrapositive cases 1, 2, 3, 4, we want not Q, then not P. All right, let's fill in our initial 2 columns for each of those truth tables. When I only have 2 statements, I do 2 by 2 for P, so true, true, false, false, and I alternate on Q. Over here, P and Q still are introduced with P as my first statement. So when I come over here, when I do the converse and I'm looking at it in the opposite order, I want to fill in my columns the same way. P is still 2 by 2 and Q is still alternating. When I come down to the inverse where I negate P and negate Q, I think back to the P and Q columns, and negate means to change the truth value. Sorry, that's an error there. That should be false, true, false, true. And then I'm using these same not P, not Q columns. I'm just looking at them in the other order, so I want to make sure I have them filled in correctly. Okay, now let's evaluate the truth value for if P then Q, our conditional statement first. Remember, our conditional statement is true unless it's a lie. It's a lie if the hypothesis is true, but the conclusion is false. So this is my false statement. The other 3 are true. What about the converse? For the converse, I've got if Q then P, so I have turned the order around. And on case 3 this time, the hypothesis is true and the conclusion is false. So that is my conditional statement that is false, and the other 3 are true. What case is false for the inverse? Well, that's case 3 as well. The other 3 are true for my inverse, not if not P, then not Q. And finally, the contrapositive, which case is false? Well, case 2, it starts true, ends up false, so that case is false for the contrapositive. If not Q, then not P. Now, I pointed out that we were going for the answer to this question from the beginning. It asks which of those statements, which of those conditional statements are logically equivalent. Well, if I look at the columns with my truth values for the conditional statement, the converse, the inverse, and the contrapositive, I see that the conditional statement is logically equivalent to the contrapositive because they are both true in every case except case 2. And the converse is logically equivalent to the inverse because they are both true for every case except case 3. So the logically equivalent pairs are the converse and inverse, and the other pair is the conditional and the contrapositive. And if you want to remember how they pair up, converse and inverse, the 2 verses, and then those long C terms, the conditional and the contrapositive. All right, let's look at the next page and talk about some biconditional statements. So those are our terms that refer to conditional statements. Now we're going to look at biconditional statements and discover under what conditions that biconditional P if and only if Q is going to be true. Well, this is true, P if and only if Q is true, when both if P then Q and if Q then P are true. So we are going to summarize the results from what we figured out. Now you can look back at your other page if you want. The first column that we have to solve here is my original conditional statement, if P then Q. And if I look at that truth table, I see that if P then Q is false for case 2 and it's true for the other cases. So I've got cases 1, 2, 3, 4. If P then Q is false for case 2, and it's true for the other 3 cases. Then we have if Q then P. Well, if Q then P is my converse, and it is false in case 3. So false in case 3, true in the other cases. Okay, now let's think about what we said. We said that P if and only if Q is true when both of these statements are true. Well, the first case, both statements are true, and the fourth case, both statements are true. So that is what that truth table looks like for P if and only if Q. Now what this comes out to be, this is the key. The biconditional statement, P if and only if Q, is true only when the hypothesis and conclusion have the same truth value. That biconditional statement is true only when both statements involved have the same truth value. Now, I did not give you a chart to fill in. I really thought I had. Goodness, I need to go back and fix that. But it says to make a truth table for each statement. Our truth table, we just need 2 cases. Or 2 statements, so we need 4 cases. So let's go ahead and just build it off of this. We're going to need P, and we're going to need Q, and then we're going to need 1, 2, 3, 4 cases. So I'm going to take a break, and I'm going to pause the video, you pause the video, and we're going to draw our truth tables. Okay, there are our frameworks for our truth tables. We're going to go ahead and just label them A, B, C, and D. We don't have labels for these different ways we turn around the biconditional statement like we did for the conditional statement. So we're just going to label these 4 truth tables as A, B, C, and D. For our original one, our first biconditional, if P, only if Q, P if and only if Q, we've got P and Q to fill in. So P is true, true, false, false. Q is true, false, true, false. You know what? Let's go ahead and do our initial 2 columns for all 3 of those other tables. I've got P down here again, true, true, false, false. I've got not P over here. So not P is going to be false, false, true, true. I have Q here and Q here. And then I have not Q. Okay, remember those are the same every single time. Now, let's look at our statements here. P if and only if Q. This is a biconditional because of the double-ended arrow. It is true when the truth values match. So it's true when both of the statements I'm interested in are true, and it's true when both of the statements I'm interested in are false. If it's one true, one false, the biconditional is false. Evaluate the other 3 truth tables the same way. You're looking for the cases where the truth values match. Okay, do you notice that some of these are logically equivalent? Do you notice that some of these are logically equivalent? Let's make a space over here to see what is logically equivalent. It's logically equivalent if it has the same truth values in the same order. I've got these 4 biconditionals that I have worked with. Which ones are logically equivalent? Well, A is true for cases 1 and 4. D is true for cases 1 and 4. So A and D are logically equivalent. So if I've got biconditionals, P if and only if Q is logically equivalent to not P if and only if not Q. And then I've got true cases 2 and 3 for both B and C. So B and C are logically equivalent. So not P if and only if Q is logically equivalent to P if and only if not Q. Okay, let's talk about these 3 vocabulary terms at the bottom of the page. We have self-contradiction, tautology, and implication. We've already been introduced to self-contradiction and tautology. A self-contradiction is what we call a compound or conditional that is always false. It's a self-contradiction if it's always false. Now, compound. My compounds are conjunctions and disjunctions. When I say conditional, I'm referring to both conditional and biconditional statements. That's how those are grouped together. All right, you know, tautology is when the statement is always true, but we are adding an additional term for statements that are always true. A self-contradiction is something that's always false no matter what type of joining I have used, whether it's a compound or a conditional. A tautology, however, just refers to compounds, and the implication just refers to conditionals. So let's get those definitions down. A tautology is a compound statement that is always true. And remember, my compound statement are my conjunctions and disjunctions. And then an implication is a conditional statement that is always true. And my conditional statement, that conditional refers to both conditional and biconditional. All right, if it's always false, it's a self-contradiction, no matter what joining term. If it's always true, I have to go back and pay attention to whether it is a compound or a conditional statement to determine whether it is a tautology or an implication. Okay, let's practice some of this by looking at some more truth tables. All right, so on the next page, we have 4 truth tables. 1, 2, 3, 4 truth tables, and we are going to determine what kind of statement it is, whether a negation, conjunction, disjunction, conditional, or biconditional. We're going to make a truth table for the statement, and then determine if it's a self-contradiction, tautology, implication, or none of these options. All right, guys, I had to pause and make some adjustments. I realized that you have this framework and structure on your page. I did not. I'm not sure how I managed to copy one without the grids. So I threw in my grids for me. For this first one, we need to determine this conditional. So let's go through maybe and label them as to what type of joining word we're using. This is conditional because it's an if-then. This next one is a disjunction, because that's what is going on outside the parentheses. The third one is a conjunction, because it is the and outside the parentheses. And this fourth one, this last one, is a biconditional. All right, we can't answer whether it's a self-contradiction, tautology, or implication, or none until we have our truth value for that final column. So let's see what columns we need to fill in. For number 1, I need to know P or Q, because that's what's in parentheses, and I need P. And to get P or Q, I'm going to also need Q. For the next one, I need this that's in parentheses, so I will need not Q, if not Q, then P. And I need to combine that with not Q. To know all of this, the other column I also need is P. Down here, I'm going to need Q if and only if not Q. And to get that, I need to compare Q to not Q. And you know what? I also need not P. So I'm going to add another column over here for not P. Down number 4, I only need the 2 things in parentheses. Now, you can make this one really, really long. I didn't draw it all out. I'm just going to put in P and not Q, as well as not P or Q, because those are my two sets of parentheses I want to compare. I'm going to use my not P and Q columns from previous. I need not P, P, I need Q, and I need not Q. I'm going to look above and use those columns from above. If you're not comfortable doing that, add on columns here. You do not need to skimp on columns if you need them right there to compare. Let's do the first couple together, and then, well, you know what? I'll just talk you through all of them because it's good for practice. We're going to start out by filling in P and Q. Those are our standard columns, just like they always are. And I'm going to go ahead and go down and fill in all those singular columns before I start. P, we know not Q. We've got not P. We've got Q. And we've got not Q. And then all the rest of the columns I have are compound columns. And conditional columns. So let's go through and let's do some of those. So to get P or Q, remember that's a disjunction. It means if at least one of them is true, then that compound statement is true. So all the cases except the last one are true here because they have at least one true statement. Let's go ahead and finish this. Then my goal, what I'm after, is this column here. If P, then Q or not Q. So I am using the first and third columns. I'm not using that second one. Remember, I'm never going to be comparing more than two columns at a time. If P, then this disjunction here. And that's a conditional. A conditional is true unless you lied. If it starts true and ends up false, then it's false. Otherwise, it's true. Well, none of these start true and end up false. So all four cases are true. If I have a conditional that is always true, what do I call that? I call that an implication. A conditional statement that is always true is an implication. Okay, let's look at the disjunction, number 2. For the disjunction, I need to first do this conditional not Q, if not Q, then P. Remember our rules for conditional. If it starts true, ends up false, then it is false. So right here, this very first case is false. The other 3 cases are true. Oh dear, I did this backwards, guys. So here's a good example of a mistake. I looked at if P, then not Q. I should have looked at if not Q, then P. I put these first 2 columns in the wrong order. So I have choices. I can either rearrange my columns so that I'm looking at them in the right order, or I can look backwards, going from not Q to P. I think I'm going to choose to look backwards, going from not Q to P. If not Q, then P. Well, this has me going from false to true, and that's fine. That's true. From true to true is fine. From false to false is fine. But down here, case 4 goes from true back to false. That the hypothesis is true, the conclusion is false. That makes that case false. I apologize that I messed up. I'm glad I caught it. I wish that somebody had been here because we were in class to help me catch it, but that's the way it goes. Okay, so I got my if Q then P column. Now I'm going to look at this disjunction. So if either this column, if not Q then P is true, or this column, not Q, is true, then this disjunction is true. I'm not using that P column. I'm using these 2 columns. And if either one is true, then the disjunction is true. And when I look through there, they all have at least one true statement. So they are all true. If I have a disjunction that is always true, it's not an implication, it's a tautology. All right, number 3. I have a conjunction going on, but before I can check my conjunction, I have to figure out Q if and only if, not Q. To figure out Q if and only if, not Q, I need to look at those 2 columns, Q and not Q. And this is going to be true when their truth values match. And as I look through there, I see none of the cases have truth values that match. So this column is false all the way down. Now I'm going to compare this column, this biconditional column, to my not P column. So that first column over here and this last column. And it's going to be compared as a conjunction. Well, a conjunction means that both of them have to be true for the conjunction to be true. And since I just filled out false all the way down in this column, that means that there's no way any of the cases can be true for the conjunction. What do we call it where we have something that is always false? Well, no matter what type of joined statements it is, if it's always false, it's called a self-contradiction. All right, this last one, remember I said that I'm going to have to, I chose, I don't have to, I could have put more columns down there, but I am choosing to go up and to look at not P and Q up there, and then P and not Q up there, and fill in these columns. I want you guys to take a minute to do that. All right, if you're not done, pause the video and then come back to me when you're done with those two columns. Make sure your two columns match my two columns. Then we have a biconditional that we are answering. Biconditional means the truth values need to match. When I look through here, I see that none of my truth values match. So again, this is a self-contradiction. Okay, this last page is kind of fun. This last page is kind of fun. We are going to be applying what we've been doing with a truth table, but to actual statements and determining the truth value of that compound or conditional statement. Okay, so let's look at these. For each problem, determine the truth value for each simple statement, then use the truth values to determine the overall truth value of the compound statement. So we're going to start by looking at each simple statement and then look at the overall statement. Number 1 says, if a cat has whiskers or a fish can swim, then a dog lays eggs. Okay, and you don't get to just say, oh my goodness, that's silly, that's false. You have to show, using truth values, if the argument is true or false. Okay, so we have 3 statements. We have a cat has whiskers, we have a fish can swim, and we have a dog lays eggs. P, Q, R. Just do alphabetical order. I have a comma here, so I'm setting it up as P or disjunction Q. If P or Q, then R. So it's a conditional statement with P or Q joined. So let's evaluate the truth values for each part of that conditional statement. I don't have room to go down, so I'm just going to kind of go over. Well, P, a cat has whiskers. That's true. Or Q, a fish can swim. That's true. Then a dog lays eggs. Well, a dog lays eggs is false. So what I have here is a conditional statement where P or Q is true or true, so that disjunction is true. I'm going from if true, then false, which is the case for a conditional where it is false. So when I go from the hypothesis is true and the conclusion is false, that's false. Let's do the next one. If a moon circles the earth and the earth circles the sun, then the moon is made out of cheese. So again, I have 3 statements. With the first 2, we've got an extra comma thrown in. I apologize for that. We've got an if and a then. Let's ignore that first column, the comma, so that these first 2 statements are joined. And then we have an if, then, are. So we've got P and Q this time, if, then, are. Let's evaluate the truth values of each of these statements. P, if the moon circles the earth. Well, that's true, it does. And the earth circles the sun. That's also true. then the moon is made of cheese. Well, we're going to go with false on that one. So again, we have a conjunction. Well, we have a conjunction in here this time, but our conjunction is true because both statements are true. So we're going from a true hypothesis to a false conclusion. As a conditional, that makes it false. Number 3, Apple makes computers if and only if Nike makes sports shoes or Rolex makes watches. So we've got 3 statements. Apple makes computers is P. And then I've got an if and only if. And since I've got that comma there, I'm going to group together the last 2. Q or disjunction R. That's what this conditional looks like. Then I evaluate the truth of each statement. Apple makes computers. That is true. If and only if, and then in parentheses, Nike makes sports shoes. That's true. Or Rolex makes watches. That is also true. So we've got this disjunction here. It is a true disjunction. We've got true, if and only if true. Their truth values match. So that conditional altogether is true. Number 4, Stan Lee wrote comic books, or if Jennifer Aniston is a school teacher, then Kanye West is a circus clown. What this should look like is P or Q, if, and then that's a if then. Oh no, I just put my parentheses in the wrong place, didn't I? Let's start over. P, that's if P, and then in parentheses, because there's my comma. Q, good grief, I'm having a hard time. P or, and then in parentheses, if Q, then R. I'm trying to do it in my head without reading it all through, and I'm failing here. So, Stanley wrote comic books as P, or, there's my disjunction, and then because of this comma, I'm grouping together this. If Q, then R. Finally. Let's evaluate the truth table of each of my 3 statements. Stanley wrote comic books. That's true. Or, and then in parentheses, Jennifer Aniston is a school teacher. No, she's actually an actress. She was on Friends. If this statement is false, Kanye West is a circus clown. That is false as well. So if false, then false is not a lie. So this is true. And we have true or true. So overall, the whole thing is a true statement. Now I'm going to pause the video and I'm going to do my PQR stuff for the remaining 4, and then we'll come back and look at it together. So you pause your video and write down all of this that I have going in green, and then we'll talk about it. Okay, I'm still struggling with this today. I started writing my trues and falses in instead of my PQs and Rs. So Independence Day is in July and Labor Day is in September in parentheses. So P and Q, if and only if R. Thanksgiving is in April. Now let's evaluate the truth values of each of those statements in this framework. My first statement P, Independence Day is in July. That is a true statement. Labor Day is in September. That is also a true statement. So I have true and true, so this conjunction is true. If and only if R, Thanksgiving is in April. Well, that's false. Because these truth values don't match, overall, this is false. Number 6, I have P or Q, if and only if R. This one was P and Q. This one is P or Q. Honda makes automobiles. That is true. Or Honda makes motorcycles. That is also true. And then I have if and only if Mazda makes cereal. Well, that's false. Now, because this is a biconditional, the truth values need to match, and they don't match. This disjunction is true. This is false. So overall, this statement is going to be false. Number 7, I've got P and Q, and then I've got disjunction or R. So let's look in parentheses first. Apple makes iPhones. That's true. And Dell makes canoes. Well, that's false. Or HP makes laser printers. That one's true. So for this disjunction, I have to have just one or the other true. This initial conjunction is false, so I have false or true. But because overall it's a disjunction, overall my statement is true. All right, the last one, if P then Q. So I've got if P then Q, if and only if R. My P statement says ESPN is a sports network. That is true. Then CNN is a news network. That is also true. Nickelodeon is a cooking network. That is false. If true, then true, that whole thing is true, and this is false. It's a biconditional, which means the truth values need to match, so they don't. So overall, it is false. Okay, let's look at this next one. Your parents make the following statement to your sister. If you get straight A's this semester, then we will buy you a new computer. At the end of the semester, your parents buy your sister a new computer. Can you conclude that your sister got straight A's? Well, no, you can't. They only said what would happen if she made straight A's, that she would get the computer. But you can't conclude she got straight A's because they didn't say what would happen if she didn't make straight A's. Maybe they had already bought her the computer. They were just hoping they could convince her to make straight A's before they gave it to her. Maybe she made A's. But either way, they didn't lie. We don't know if she made A's or not. All we know is she got the computer. So it's either if true, then true, or if false, then true. And either one of those is fine. The other one of those is true for that conditional. Now we've got a challenge puzzle down here. I am not going to go through this with you. I want you guys to work on that. There's going to be a written assignment for 3-3. And if you will turn in the answer to the challenge puzzle, I will give you a bonus for the written assignment for 3-3.